I'm shortening that. And then finally you get to this server, right? So that's what we're actually looking at. We're going to look at the latency there, the latency here, the latency here, the latency there. But I want you to bear in mind that some of this is repetitive because every time you go to a service cloud, you get those additional delays in the path as well. So let's talk about this workstation piece. Well, what's the workstation doing? Well, he's running hopefully approved applications. Maybe you have a browser open. Maybe you're running J client or C client. Maybe you have Word open, whatever. There's a bunch of open applications that may not be executing, but the operating system is still serving them. So if you want to get to that lean and mean state, you should minimize what you're asking your local workstation to do. And that's all on the approved stuff. Now, there may be a bunch of things happening on your workstation that maybe aren't approved, or maybe they're approved, but they're not a good idea for performance. Internet radio, for instance, is horrible. Not only on your machine, but on the wire, because every packet you listen to, every sound you hear is coming in an IP packet. It has to be sent over packets. That hurts. Interactive gaming, man, really bad. Some of these remote file shares, GNU and things like that have a lot of give and take from remote machines. Very bad. And I'm saying unapproved with a question mark because maybe you don't have a policy that says you can't do this, but if you're seeking the holy grail of workflows performance, it's not a good idea. Your local firewall, remember I said some we can control, some we can't. We got to learn to live with firewalls. But every time a packet goes into a firewall, it has to be dissected and thought about. There has to be logic that makes decisions on it. That hurts sometimes in terms of processing time, but it's required. So we can't get rid of that, but it's adding to the equation. And then there's everybody's favorite, the viruses and spywares that are out there. And then finally, your hard drive gets fragmented over time. It's a good idea to defragment because the time it takes your CPU to access the drive is in the latency. It's processing time. So some we can control, some we can't. Most of this on your workstation is under your control. For instance, if you have a firewall on site, turn off your Windows firewall on your machine because it's probably doing redundant duty. So the idea is, if you really want this thing to perform well, get lean and mean on what you're doing locally. All right, so let's move into the next piece, which is the local area network. These are where the latency's coming here, as we said. Every time your packet goes through a local switch, every time it goes through a local firewall, every time it goes through a local router on your local area network, it's adding latency. And then finally, it's competing with all the other users of your network, which is normal. It's normal. But if you're competing against somebody if you're on workflows and somebody's running full motion video down the hall, that's going to hurt, and you're going to notice it. So some of this is under your control or not. The main part is configure your network so there's no extra hops in it. All right. Again, just to ground you where we are, we've talked about this. We've talked about this. Now we're talking about the provider. What happens in the provider world? Same thing. There's switches and firewalls and routers and all kinds of equipment that you never even know about, the internals of their long-haul networks that your stuff goes through, plus all the external traffic load for the customer base. Here's a real-world example. You're in one town, there's two towns, and you're served by the same provider. You're used to a certain performance level in your town. And then in the next town, there's a growth spurt, and all of a sudden, your provider picks up a whole new customer base there. Totally different town, but your packets and their packets meet up at the provider's network. So that this is a huge source of load, and the idea in the perfect universe is the providers are building networks that can absorb the growth. But they don't always do that. Sometimes they do it after the fact. All right, again, ground yourself. Let's say there's a whole other path out of there. These people are being affected by the second group of people all the way at the provider network, the local provider network. Finally, you get to the server itself. Well, the Cersei server, it's keeping multiple client sessions open, so that's why you can all be on at once, but that takes processing time. Maybe it's doing some firewalling. Maybe it's been affected by a virus. Maybe it needs some defrag or something else. Maybe it needs more memory or something like that. However, that thing is configured as to the latency equation, which will affect your response time at your machine. So now we're all the way to here. So latency, yeah. Latency, yeah. All of that stuff actually adds to the delay, and you will notice that on your machine, right? So when I said earlier it's a complicated issue, it is. And each one of these things have to be running at maximum efficiency for you to have maximum efficiency at the response level on your application. Remember, somebody hits this with a backhoe. Is that service affecting? Yeah. You don't have a wire anymore. But it can be service affecting just by load, just by normal load, things that are totally beyond your control. And the idea is to start to figure out where that problem is. Okay? But now we're getting into some nasty stuff. More detail. Okay, so we just got through talking about latencies. We're all in agreement that there's physical latencies and there's logical processing latencies, and now you know where they are. Now it turns out, once you're inside these machines, either your workstation or the Testi server, there are protocol issues. Now, does everybody understand that the internet works on the IP protocol, right? All right. So we need to have a discussion about stack behavior, and then we're going to talk about application behavior on top of the stack. This is a classic representation of what this looks like. Here's workflows. And here's the server application. So this is your machine, and this is the Testi server. Every machine that runs in the TCP/IP world has what's called a protocol stack in it. This is a program. These are computer programs, right? And they're in hierarchical stack form. So your client application talks to this piece of code on your workstation called the TCP/IP part of the stack. And it knows about things like port numbers, which allows the Testi server to identify everybody in this room individually. The TCP/IP layer talks to the IP layer, and it's the IP layer that knows about things like routing, IP addresses, all that layer 3 stuff. Still within this machine, that part of the stack talks to what's called the data link layer, which ultimately talks to the LAN, the network card, in this machine, right? The actual hardware. And then the data link layer goes to the physical layer, which is actually the wire. So this is all logical until you get to the LAN card. It's all software. And then you're on the wire, right? And then the server application has the exact same configuration. It has a TCP/IP stack, right? Now these virtual connections are shown as such for a reason. Your client, do you agree that the client talks to the server at a software level? Do you agree with that? They don't talk directly to each other though. They talk to each other virtually through the stack. Do you agree that your TCP/IP layer in your workstation talks to the TCP layer in the server? It has to. Not directly, but through the stack. So your packet is launched here, goes to TCP, is processed, goes to IP, is processed, goes to data link, is processed, gets sent to your LAN card, goes out on the physical path, comes on the physical path to the server, talks to that server's LAN card, which is passed up to the IP stack in the server, which is passed up to the TCP part of the stack in the server, up to the server application. That happens every time you send a packet. Every packet, whether it's 32 bytes or the maximum size, every packet gets processed like that. Furthermore, every device in the path that processes that packet does the same thing, right? So tell me something about this model. Inherently, there's a lot of what? Latency. It's normal. It's normal. And by the end of this talk, you're going to leave here going, I don't even know how it works in the first place. It's so right. Let's talk about this TCP stack diagram. Remember, every entity, computer, workstation, or server that we're talking about has a stack. Well, what does the stack do? It supports port-to-port connections that allows you to talk to an individual port on the server. Remember, the server keeps track of each and every one of your sessions by port. TCP is an acknowledgement-based protocol. What that means a lot of things. What it means that's really important, though, is every time a TCP sender sends